Okay, we're going to start looking now at our last three simple machines. We're going to look at the inclined plane, the wedge, and the screw. Now if you remember, we said that the inclined plane was kind of the base simple machine, and then the wedge and screw are simple machines that are kind of based on the use of the inclined plane. You're just using the inclined plane in a different format. So an inclined plane, let's move this out of the way so you can see. Inclined plane is a flat surface. It's set at an angle or an incline, and it has no moving parts. What you do is you take and you can lift these objects up by pushing it up this incline or by pulling it up the incline. So instead of lifting the box directly up, you can get to the same point by pushing it up the incline and then using the weight supported by the incline to take up some of the load. The ideal mechanical advantage, as we've already said, is the distance the effort travels over the distance the resistance traveled. So in this instance here, the distance that the effort travels is going to be the length of the ramp, or basically it's the slope of this incline right here. The distance the resistance travels, the resistance is basically going from down here up to here, so it's really only traveling the height of the incline. So the ideal mechanical advantage then is going to be the length of the ramp or the slope divided by the height of the ramp. So looking at our picture up here on the right, we can say that the ideal mechanical advantage for this inclined plane then is going to be ideal mechanical advantage is going to be the length of the slope is 15 inches and the height of that slope is 4 inches. So if we do the calculations on this, 15 divided by 4 is 3.75. So the ideal mechanical advantage is 3.75. Now the actual mechanical advantage, remember we said, was the resistance load divided by the effort. So the actual mechanical advantage for the inclined plane above, notice the weight in this cart is 50 pounds, so that would be the load, resistance. The effort needed to push it is 20 pounds. So the actual mechanical advantage is equal to 50 divided by 20. And if you do the calculations for that, that is 2.5. So the actual mechanical advantage is much lower than the ideal mechanical advantage. And the reason for this is due to just the friction of the pulling the cart up the hill. Maybe there's some friction with if you're pulling it using a rope as it's wrapped around the pulley. So the efficiency is never going to be 100%. So calculating the efficiency, remember we said it's the actual mechanical advantage divided by the ideal mechanical advantage times 100, and the 100 allows us to put it in percentage form. So the actual mechanical advantage was 2.5. The ideal mechanical advantage was 3.75. If we take that and multiply that number by 100, we end up, if we calculate that, at about 67%. So not great, but it's not bad either. So 67% efficient is what this inclined plane that we have in our example has. The wedge is an inclined plane, but instead of being stationary like the inclined plane, we actually move the wedge. So if you think about it, you have the weight on the ground and you kind of push the wedge underneath the weight, and as you push it under, it causes it to lift up. So it functions as a moving inclined plane. It tapers to a thin edge at the bottom so that you can get it underneath whatever load you have. And we use it for splitting, for raising heavy bodies, or for actually tightening up certain devices. So, and we do that by driving the wedge in. So here's the effort that you're going to put in is right here. You're going to push this wedge in, and it's going to either split the material apart or lift the material up. Once again, the ideal mechanical advantage is the distance the effort travels over the distance the resistance traveled. So in this example here, instead of being the distance the effort traveled being the length of the wedge, the slope, is actually the overall length of your wedge. So in this example, from this point up here to the tip is 10 inches. So that would be the length, and it's always the length perpendicular to whatever we called our height. Basically, our height is the thickness of the wedge. So our ideal mechanical advantage then is the length perpendicular to the height over the height itself. So in our example right here, we have the ideal mechanical advantage of this wedge. Let me see if I can get my pen writing again. The length is 10, the height is 3, and so therefore you end up with that, calculating this out, is 3.33. Okay? So that would be the ideal mechanical advantage. Now with a wedge, because you're actually pushing this in between materials, there's a lot of friction that's going to build up in this. But once again, the actual mechanical advantage is the load, Fr, so that's the resistance load, over Fe, which is the effort. Okay, so the effort force. So we have the force of the resistance over the force of the effort. So in this example at the right, the actual mechanical advantage, notice you have to push down with 250 pounds, but you end up getting 700 pounds worth of resistance. So you're able to push 700 pounds up or apart with only 250 pounds of force. So let's go ahead and calculate this mechanical advantage. So the actual mechanical advantage then is going to be 700 pounds, that's our resistance force, divided by 250 pounds, that is our effort force, and that comes out to be about 2.8. So we had the ideal mechanical advantage of 3.3, the actual mechanical advantage of 2.8. So calculating the efficiency, the actual mechanical advantage, 2.8, divided by the ideal, which is 3.3, times 100, is going to equal 84%. That's actually really good to have the efficiency of 84% for a wedge. Usually it's a lot lower because there is so much friction force involved in pushing the wedge underneath the weight or actually splitting the material apart. Our next mechanical simple machine is the screw. Now, the screw is just an inclined plane. If you think about it, we took this inclined plane and we wrapped it around the cylinder, and so then we form this path that basically spirals down the cylinder, and we call that path the pitch. Now, if you think about how a screw operates, we rotate the screw, and as you rotate the screw, it goes into material, so it's going down or up, so it's a linear motion that is created by turning, so a rotary motion. So some of the properties of a screw is it allows you to change from a rotary motion, turning around, you rotate the screw around, and into a linear motion. So as it's turning around, it pushes down into the material. We use it as a threaded fastener, so it can join two objects together. It has a very large mechanical advantage. However, there's a huge amount of friction loss because look at how much surface area there is for this screw as it going around and around and around. There's so much friction involved, with the two surfaces coming in contact with each other that we end up having a huge amount of friction loss. Okay, now there's a lot of things involved in to identify your screw. So let's go over here first and look at the thread information. Okay. Your thread is defined by 3 different categories. And you'll see this if you ever go to Home Depot and look at the bins of screws. They're all classified by 1, the diameter. That is the actual, if you took some calipers and measured across, that would be the diameter of the screw itself. The next thing is this number here, in this example 13, and that is the number of threads per inch. So if you started counting and you had a 1-inch screw, you would count 13 threads in that 1-inch length. The last thing we don't really concern ourselves very much with it, but basically it describes the thread, whether it's coarse or fine, and that's not a big concern. The first 2 numbers are our biggest concern that we have to look at. Now we talked about the threads per inch. We define pitch as the distance between the threads, or the linear distance traveled with one rotation of the screw. So if we have 13 threads per inch, then the pitch, or the distance between the threads, is going to be 1/13. So the linear distance that a screw will travel as you rotate it one time is 1/13 of an inch. So when you say, how far will a screw with 13 threads per inch move linearly? If turned one rotation, you're going to move 1/13. So it's basically 1 over the number of threads per inch. Now the effort arm distance is going to vary. It is actually the distance that's traveled by you can hear the trash truck going by. The distance traveled by the wrench handle, or the distance traveled by the diameter of the screwdriver that you're using. So it's going to vary. Once again, ideal mechanical advantage is the distance the effort travels over the distance the resistance travel. The effort is going to travel in one rotation of the effort arm. It's going to be the circumference of the effort arm. So if you attach a wrench to this, it's going to be the length of the wrench. If you attach a screwdriver to this, it's going to be the circumference of the screwdriver handle. Right? So the circumference depends on what you're using to attach the screw with. The distance the resistance traveled is always going to be the same. It's the linear distance traveled during one rotation of the effort arm. So that's going to equal to the pitch. So as your wrench goes around one time, the screw rotates one time and it drops a distance of whatever the pitch is equal to. So the ideal mechanical advantage is the circumference divided by the pitch, and it's the circumference that the wrench, or the length of the wrench. So we have, for this one right here, if we use the ideal mechanical advantage for the screw in this picture, applied by an 8-inch long wrench. So let's calculate what the ideal mechanical advantage is. So we have ideal mechanical advantage. The circumference the wrench travels is going to be 2 times pi times the wrench handle length, which is 8. So 2 times pi times 8. The pitch for this screw, notice there's 20 threads per inch, so it'll be 1 over 20. Okay. Now this is equivalent to 20 times 2 times pi times 8, which is approximately 1005. Okay, now look at this. This is a huge ideal mechanical advantage. There's no way you're going to actually see something like that. And the reason you don't in the actual mechanical advantage so much lower is because of that friction loss when you put two of these surfaces next to each other. There's so much surface area for that, those screw threads. So let's look at an example of the actual mechanical advantage for this. Notice the force due to the resistance is going to be 1,200 pounds. Basically what it's saying is that if I wanted to push this down, let's see if I can push this down through a piece of material, it would take 1,200 pounds worth of force just directly down in order to move it. However, by rotating it using our 8-inch long wrench, it only requires us to apply 35 pounds of effort force. So the actual mechanical advantage then is going to be 1,200 divided by 35, which is equal to, let's do these calculations, approximately 34.3. Okay, so that's a big difference from the 1,005 that we came out with for the ideal mechanical advantage. So look at the efficiency then. The actual mechanical advantage is going to be 34.3, and we divide that by the ideal mechanical advantage, and we said that was 1,005. You multiply that by 100 and do that calculation, you come out with approximately 3.4%. 3.4%. Right, very low efficiency for a screw. Once again, the efficiency is so low due to friction. There is so much friction loss in this screw system that we have to, that it really takes out from the ideal mechanical advantage. All right, the last thing that we need to just look at, and we're just going to look at this briefly, we'll get into more detail later when we get into compound machines. But when you have compound machines, basically they're simple machines working together to complete a task. When you have a compound machine, what you need to do is to calculate the total mechanical advantage is you take the mechanical advantage for each machine and you multiply it together. And that's all the detail we're going to go into at this point for that. And we'll do more examples of compound machines later when we actually start our project involving compound machines. And that's it on our simple machines.